Welcome to the 10th lecture of our Natural Disasters course. In this lecture, we'll be covering hurricanes. So a hurricane is a large tropical cyclone. So unlike the cyclones that we have discussed when talking about severe weather, hurricanes, they form within one large air mass and not along a front. So the storms that most of us experience, say in North America, that track across the country, those are called frontal cyclones, and they form along a weather front, which is a boundary between one or more air masses of different temperature and humidity. Where a hurricane is a cyclone that forms within one large uniform air mass. They don't form along fronts. Hurricanes are extremely efficient heat engines where they convert the energy that is the latent heat of vaporization, it's in the water vapor above warm tropical oceans, into very high wind speeds. So they convert that energy in that latent heat of vaporization that's in that water vapor into the kinetic energy of moving wind. And they push massive amounts of water on shore, as what is known as storm surges, up to 6 meters over sea level, which are damaging, but not the most destructive part of a hurricane. The most destructive and lethal part of a hurricane are the heavy rains as they move inland, as we'll see. They cause significant amount of flooding. So hurricanes are just one of the means, a very extreme means of transporting excess tropical heat to the mid-latitudes. So what are the requirements for a hurricane to develop? Well, we have to have enough water vapor in the air. In order to have enough water vapor in the air, the sea surface temperature has to be at least 27 degrees centigrade, which is 80 degrees Fahrenheit, in the upper 60 meters of the ocean. The air must be warm, humid, and unstable. And unlike with the frontal storms, with hurricanes, we need very weak upper level winds, preferably blowing all in the same direction as the storm is developing and moving. So we need actually, for hurricanes to develop, no wind shear. So we want the wind all moving in the same direction. Where for frontal cyclones to form, especially for tornadoes to form, we need wind moving in different directions at different altitudes. That is not the case for hurricanes. We need zero wind shear, or very little wind shear, which is wind moving in different directions at different heights for them to develop. So hurricanes, they start as a tropical disturbance, which is a low pressure anomaly that finds itself over these warm tropical waters. Now, this low pressure anomaly, it could be a storm that existed over land and then the wind blew it over the ocean, or it can just be a low pressure anomaly that begins over the ocean, the tropical ocean, but just a low pressure anomaly. And that low pressure, remember, low pressure is created by warm, moist air rising. And as it rises, it takes the water vapor up with it, the moist air, the water vapor, and then it adiabatically cools. Now, water vapor condenses out, adding heat to the upper atmosphere, decreasing its density. By warming the air, you make it less dense, making it want to rise with more vigor. So as the air aloft wants to rise with more vigor, it lowers the pressure even more. And as the pressure lowers, what happens is the air surrounding the low pressure system is pulled in with more vigor. So it creates this positive feedback loop. And so the tropical disturbance, that low pressure anomaly, as it begins to go through this feedback loop, the pressure drops and the wind speed begins to increase until eventually it becomes what's known as a tropical depression. So tropical depression is categorized by a certain barometric pressure and a certain wind speed, and receives an identifying number. So in this, from going from a disturbance to a depression, surface winds, they strengthen and flow around and into a core. It rotates counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. So the converging winds at the core, they flow up the central core like a chimney, sending warm, moist air into the stratosphere. As I said earlier, that rising moist air cools to the dew point, and then the water vapor condenses, releasing that latent heat of vaporization. That released heat warms the surrounding air, makes it less dense, and makes it want to rise with more vigor, so it creates stronger updrafts, which increases the rate of upward flow of warm, moist surface air. And so this tropical depression then transitions into a tropical storm once the wind speed exceeds 63 kilometers per hour. And then the tropical storm is then recategorized as a hurricane when the wind speeds exceed 119 kilometers per hour. Such an arbitrary number, right? 119 miles per hour. Sorry, kilometers per hour. Why? Well, something important happens at that wind speed. As more wind blows into the center of the tropical storm, it becomes difficult for all the wind to reach the center and spiraling up as a cylindrical wind mass in the center of the storm. So when the surface wind speeds reach about 119 kilometers per hour, none of the wind actually reaches the center. The wind spirals up in a cylinder around the center, and it creates this calm, clear center known as an eye. So it's when the wind speeds reach 119 kilometers per hour that an eye develops. And once the tropical storm develops an eye, it's then considered to be a hurricane. So inside the eye, there's cool high altitude air, it sinks and has absorbed some of the moisture. The eye walls, where the air is spiraling and moving up in this cylinder shape, that's where the strongest winds exist. So here you can see the low pressure, the air is rising. And this rising low pressure is pulling surface air in. And this warm surface air, it's very warm, very humid, so it has a lot of energy in it, and that's how the storm is feeding itself. As that warm, moist air rises, it cools, condenses, and the latent heat of vaporization is released, heating this air, making it want to rise with more vigor, decreasing the pressure and increasing the wind speed. All right, so you can see here, this is the pressure. You can see how the pressure is at a minimum right at the eye, at the surface. You can see the temperature kind of slightly increases here because this warm air is rising there. So you can see the lower pressure at the center of the eye. So the hurricane, it transfers heat from tropical seas to the core of the hurricane. Huge amounts of latent heat are released as the air rises. Sorry, I apologize for the dogs. I thought they could be quiet. Obviously, a creaky door set them off. I'm sorry. So huge amounts of latent heat is released as this air rises, as I've been saying. And this transfer of energy, basically the heat from the ocean being transferred into the atmosphere, generates energy at 200 times greater the rate of worldwide electricity generating capacity. So the amount of energy that's being converted from sensible heat, which sensible heat is heat associated with temperature, where latent heat is the heat associated with phase change. So the amount of heat being transformed from one form, heat in the ocean, to another form, that's the kinetic energy of the wind, the motion of the wind. It's significant. It's one of the most powerful heat engines on our planet, if not the most powerful heat engines on the planet. So I've already mentioned the difference between hurricanes and high latitude storms. But the main energy source is the latent heat released from water vapor condensation. They weaken rapidly when they move onto land, hurricanes do, because their source of energy is the very, very warm, humid air that forms over warm water. They're not associated with fronts, and their weaker high altitude winds means stronger hurricanes, right? Where stronger high altitude winds means stronger frontal cyclones. Hurricane winds, they weaken with height, and air at the center of the eye sinks downward. So hurricanes have different names in different parts of the world. In the Indian Ocean, they're referred to as cyclones, and in the Western Pacific Ocean, they're referred to as typhoons, but they're all the same phenomenon. So hurricanes, they form between 5 degrees to 20 degrees latitude, north and south hemisphere, and then they travel to higher latitudes. They do not form along the equator because the Coriolis effect is 0, and they cannot cross the equator once formed because they'd have to rotate in the opposite direction. The storm would have to stop and then begin to rotate in the opposite direction. Plus, the Coriolis effect always deflects the storms away from the equator. And so the 5-degree limit is due to the Coriolis effect. They can't form any closer to the equator than around 5 degrees north or south. The 20-degree north and south limit, that's due to the temperature of the sea surface, of the ocean water. Now, as we'll see, as global temperatures and sea surface temperatures are increasing, that range at which hurricanes can develop is also increasing. So here's a map of hurricane tracks. So you can see hurricanes that we are most interested in here in the eastern part of the United States are those that form over the North Atlantic. So they form over the North Atlantic, and then they track across the Atlantic, and some of them can turn and just move out across the North Atlantic Ocean, and some of them do not turn as fast, and they make landfall on the United States. So there's an average of 84 tropical cyclones, hurricanes, typhoons, or cyclones each year, and about 10 of them in the North Atlantic, Caribbean Sea, and Gulf of Mexico region. So that's about 12%. So 12% of the tropical cyclones are in the North Atlantic basin. The Simpson Scale is used to assess the strength of a hurricane. So we have 5 categories in the Simpson Scale, from category 1 to category 5. Category 1 is the smallest hurricane, where the wind damages trees and unanchored mobile homes. Then they increase in size and magnitude to the category 5, where there's severe damage to buildings. Major damage to buildings less than 5 meters above the sea level, within 50 meters of the shoreline, and small buildings are overturned and blown away. And you can see, the larger the storm, the lower the pressure, right? The higher the wind speed, the larger the storm surge. So from 1851 to 2006, the U.S. Gulf and Atlantic coastlines have been hit by 279 hurricanes, 3 category 5 and 18 category 4. Most form in late summer when the sea surface temperatures in the North Atlantic are at their warmest. So due to the high heat capacity of water, it takes a while for the water to warm. So very early in the summer, the water isn't warm enough yet. So it's later in the summer and in the early fall that the sea surface temperatures in the North Atlantic are at their highest. So that's peak hurricane season in the North Atlantic. Might be wondering, well, how do we know hurricanes that made landfall in U.S. and Gulf back in 1851? Sorry, we were here 1850. Well, there's written record for 1851. Year 851. Well, it's because hurricanes, the storm surges, they wash sediment inland and deposit sand inland. And so in the geologic record, we can see historical evidence of storms in the past. And so if we go to coastal marshes, we do a core sample, look at the sediments, we could see evidence of storms occurring in the past. So this is the the frequency of hurricanes and in North Atlantic, and you can see that August, September, October are peak season. And why is this? Well, that's because, as we said, that's whenever the water in the North Atlantic is at its warmest. So there's the most energy in the water from being warmed by the sun all summer long. So we have different types hurricanes. One's known as the Cape Verde type hurricane. It usually begins as what's known as an easterly wave, which is a low pressure anomaly that moves across the tropical Atlantic. And so it may gain tropical storm status near Cape Verde Islands off Africa. That's why it's given that name, Cape Verde type hurricane. It's blown westward by the trade winds that blow from east to west, and it gains energy by moving across the warm Atlantic Ocean. And then it is directed north by the Coriolis effect. So an example of such storm was Hurricane Andrew in 1992. Began as a thunderstorm over West Africa, August 13th. Moved out over the Atlantic Ocean as a rotating low pressure air mass. So here's just a thunderstorm. There's a low pressure air mass. Intensified into a tropical storm by August 17th. Reached the Western Atlantic on August 21st. As upper level winds died down, allowing clouds and winds to build, and as high pressure to the north, there's high pressure up here, prevented the storm from continuing to turn to the north and forced the storm to kind of move more westward over even warmer water. So if it would have continued to move up here, it'd be over cooler water, it would have de-escalated. But it stayed over this warm water, which caused it to continue to increase in intensity. August 22nd reached hurricane strength. August 24th hit northern Bahamas, wind speeds of 240 kilometers per hour. August 24th crossed the southern tip of Florida with a 25-mile wide path of over 350,000 people. Their homes were significantly damaged and wind speeds of 250 kilometers per hour. So 33 people were killed, destroyed a total of 80,000 buildings, completely destroyed. Moved over Florida over into the Gulf, where it was once again over warm water, so it regained energy. It hit Louisiana with 190 kilometer per hour winds on August 26th, killed an additional 15 people, and spent the remaining of its energy as dropping heavy rains over Mississippi. In the end, there was $30 billion in damages. Up to that point, it was the most destructive storm in U.S. history. So most of the damage was a result of poor construction. It was Hurricane Andrew really caused some significant changes in the building codes for Florida and other parts of the Gulf Coast to make sure that buildings aren't as vulnerable to hurricanes. So the paths of hurricanes are influenced by several factors, mainly The trade winds, trade winds blow from east to west at low in the tropics. And so they blow the cyclones in the northern hemisphere or everywhere to the west. Then the Coriolis effect, it turns them, deflects their path to the right in the northern hemisphere, to the south in the southern hemisphere. And as they get further from the equator, the Coriolis effect is stronger, and so it turns them even more. So another factor that influences the path of hurricanes in the North Atlantic is the Bermuda High. It's a North Atlantic high pressure zone. If this high pressure zone is small and to the north, most hurricanes are allowed to turn and completely miss the coastline, follow path A. If the high pressure zone, the Bermuda High, is strong and extensive, it doesn't allow the Coriolis effect to turn the hurricane as effectively, and so it usually makes landfall along the eastern seaboard. And if it's located further to the south, that Bermuda High doesn't really allow the hurricane to turn that much at all, directs it into the Gulf, and it causes the hurricane to hit the Gulf Coast. So it's also the location, the extent and location of this high pressure zone known as the Bermuda High. So the Bermuda High is part of what's called the North Atlantic Oscillation, where it's a decade shifting of atmospheric pressure over the ocean. So it shifts roughly at a frequency of 10 years. 1950s, the East Coast was mainly getting hit by hurricanes. But however, in the 60s and 70s, it was the Gulf Coast is getting hit by hurricanes. So that shows you the North Atlantic Oscillation, the Bermuda High, was in one state in the 1950s and in a different state in the 60s and 70s. It was strong, but still to the north in the 50s, and it was further positioned further south in the 60s and 70s, steering the hurricanes into the Gulf. So hurricane forecasts, whether a season is going to be very active or not, can be based upon several factors. So if you have a wetter western Sahel region, which is the western part of Africa, warmer sea surface temperatures and low atmospheric pressure in the Caribbean, then we have a recipe for a higher, more active hurricane season. However, if it's drier, there's going to be less in Western Africa, there's going to be less storms. There's cooler sea surface temperatures, there's not as much energy, and there's a higher pressure in the Caribbean. There's not as low pressure, then we're not going to have fewer hurricanes. It's going to be a not as active season. Here we can see the annual probability of named storms being in each area between June and November. This is probability, so there's a 55% chance there's going to be a named storm in this region between June and November. So that's greater than 50. So that's a coin flip. So I think this area is 50. So every year there's a 50% chance in this area there's going to be a named storm there. And that includes most of southern Florida. So every year there's basically a coin flip's chance that there's going to be a named storm, which a named storm is anything that's a tropical storm or higher. Not just hurricanes get names, but tropical storms get names too. And here's the annual probability of hurricanes and great hurricanes making landfall along 50-mile segments. So if you look here, we're about right here. So the annual probability of a storm making landfall here is about, around 6%. And then the outer ribbon is great hurricanes. And so there's, a much lower percent chance of a great hurricane, category 4 or 5, making landfall. However, in Florida, you could see the chances of a hurricane making landfall are much more significant, right? And even for a great hurricane. So how hurricanes get their names? So they use alternating male and female names, and it's a 6-year cycle. So for example, this is an example of, I mean, these are the after 6 years, they repeat them. So, you know, some of these names might seem familiar to you. Sometimes if there's a really notable hurricane, they will retire that name. And so Sandy, it's question. I don't know if they're going to use Sandy again. It might be retired because of its impact. But you know, in recent, remember Hurricane Harvey hit Texas, hit, you know, mainly Houston. That's Harvey on the list. And there's you know, a lot of these other names that you hear them during hurricane season. These different names you mentioned, especially sometimes not so many. You know, Andrew was the except Andrew's no longer on the list because it was retired. Andrew was one of the first major named storms because it was Andrew. So it's surprising. It was not often that that first one is that big. So the decade of the knots from 2000 to 2009 was an exceptionally bad decade. So 2004, Florida was hit by 4 hurricanes. Japan was hit by 10 typhoons. And the first documented hurricane hits in the South Atlantic. It made landfall in Brazil. In 2005, the hurricane records were broken in North Atlantic Basin. And is this increase due to human activity or natural variation? Well, the total increase in the total energy release by hurricanes is higher. This is probably due to an increase of energy in the sea surface temperatures and increased amount of water vapor in the lower atmosphere. And this is likely due to global warming, right? So just as our climate warms, the sea surface temperatures are warming. There's more energy in the ocean to fuel these hurricanes. So we're having more frequent, more powerful hurricanes. So records made during the 2005 Atlantic hurricane season, there was 28 named storms. The old record was 21. 15 hurricanes. The old record was 12. 4 major hurricanes hit the U.S. The old record was 3. And there were 7 tropical storms before August 1st. The old record was 5. The most costliest U.S. hurricane is Katrina, and Mexico is Wilma. So hurricane damages and deaths. Deaths are down in recent decades. You know, this is partly because of our increased ability to project the storm track and evacuate people. Hurricane damages are up. That's because there's larger, more expensive homes on coastlines. The destruction and deaths are caused by the winds, storm surge, and the heavy rains and inland flooding. Here you can see the most deadly hurricanes in the United States, 1900 to 2012. I had 8,000 deaths in Galveston, Texas in 1900. And then in 1928, 2,500 deaths in southern Florida. Then Hurricane Katrina in 2005, that was the most deadly recent one, 1,836. You can see the numbers have dropped off, and not necessarily with time, but you can see that the most deadly ones besides Katrina were, you know, the early part of the 20th century. Here's the hurricane in 1938, hit New England, especially Rhode Island, and there were 256 people killed in that hurricane. And it's interesting, different parts of Rhode Island, you can still see ruins from the structures that used to, that were destroyed during the hurricane. So years of the 17 deadliest and costliest U.S. hurricanes between 1900 and 2005. So in 1900 to 1915, there was 5 of the deadliest. And then you can see as time goes on, there's fewer and fewer and fewer deadliest. Here, this was Katrina. That's the one, the most recent one. However, the most costly, those skewed towards the recent, right? So they're becoming less lethal, but more costly, right? If you normalize the costs, though, as far as adjust the numbers for inflation and compare them all in terms of 2006 US dollars, right? They're still even becoming slightly more costly just because there's more property and being destroyed. And here's the 22 costliest hurricanes striking the United States between 1915 and 2012. Damage in billions, and then the hurricane category. So this TS, that means it's a tropical storm, so it was below a Category 1 hurricane. So storm surge, it's a rise in sea level under a storm due to the winds that push water ashore. So and pile up the water in a mound that's higher than normal sea levels. The storm surge is higher on the right-hand side of the eye in the northern hemisphere and the left in the southern hemisphere. That's because the storm turns counterclockwise to the right-hand side of the eye. The wind is moving in the same direction as the storm. So the winds pile up the water more effectively on the right-hand side of the eye than on the left-hand side. And then also the storm surge is partly caused due to low atmospheric pressure, which is kind of acts like a vacuum, kind of sucking the water up into a mound. And so there's also large waves blown by hurricane winds. There's, besides the storm surge, which is just a large mound of water that's pulled inland, there's also large wind waves. And sometimes if the storm surge hits it coincides with an astronomical high tide, being more devastating. So then there's the heavy rains and inland flooding. After moving on land, there's no more water vapor being fed into the storm, and so it begins to lose strength. And then all that water vapor that's in the storm begins to precipitate out. There's huge volumes of water falling as precipitation as the storm is dissipating, and causes massive flooding. And so this causes the majority of deaths, inland flooding. So you can see inland flooding is responsible for 59% of deaths. Then the wind, storm surge, offshore, those are people on boats and so forth, tornado and others. And actually, the number of deaths due to hurricanes are decreasing, and the number of deaths indirectly as a result of hurricanes is starting to rival that of the hurricane itself. And by indirectly, I mean people using things like generators to make electricity. They put the generator too close to their house or too close to a tent that they're using, and people are dying from carbon monoxide poisoning. So actually those things are becoming just as lethal as the hurricanes themselves, because hurricane deaths are decreasing to the point. So I know there's been a lot of public education in areas afflicted by hurricanes about how to stay safe when using things like generators, because those indirect deaths are starting to creep up and to be, comparable to the direct deaths from hurricanes. So hurricanes in the Gulf of Mexico coastline, Galveston, Texas, in September 1900, that was the deadliest natural disaster in U.S. history. Galveston was the wealthiest city in Texas, 38,000 residents. They're given warning of a hurricane, but many did not evacuate. So a Category 4 hurricane hit a high tide with 200 km/h winds. And the highest point on the island, because Galveston is a coastal island, was flooded to a depth of 30 centimeters. So 6,000 people were killed, but many survived 10-meter waves by crowding in a lighthouse. The city constructed a seawall, brought in sand to elevate the land, But there's another hurricane in 1915, killed another 275 people. And then there was Hurricane Katrina in 2005. There's a tropical on August 24th, tropical air mass over Bahamas, first cataloged as Katrina. And then the 25th of August, it grew to a hurricane 2 hours before crossing Florida. While over Florida, it lost some strength, but began to grow again rapidly after it passed over Florida and was over the Gulf. And it actually doubled in size, increasing its wind speed to 280 miles per hour. August 26th, models forecast the 17% chance of a direct hit to New Orleans. August 27, warnings were issued, residents began to flee. August 28th, there was mandatory evacuation, which ordered 1.2 million residents to evacuate. All roads were set to exit. So, you know how interstates have, lanes going in two different directions? Well, all the roads were in the same direction, and that was away from the city. August 29th, 2005, the hurricane came ashore east of New Orleans. Wind speeds 195 miles per hour, pushed enough water to breach the levees. It caused overflow of canals and flooded 80% of low-lying New Orleans. 1,500 of 100,000 residents who did not evacuate were killed. So just so you know, whenever there are these, they can never force an evacuation, but whenever there's a mandated evacuation, what that does is that allows the government to not be responsible for rescuing people. So whenever there's a mandated evacuation, you can stay if you want, but often it's suggested that you take a Sharpie and write your name and some other identifying information on your forearm in case they find your dead body, because no one is going to come rescue you. That's the nature of forced evacuation. It's because the government is not going to put first responders' lives in harm's way. And so you never have to stay in a forced evacuation, though it's highly recommended. And if you do stay, you are on your own. So where the Katrina caused deaths and destruction and surprise, well, a hurricane like Katrina was anticipated for years. There were special reports in the New Orleans Times in 2002, among others. And in September 2004, Hurricane Ivan narrowly missed hitting New Orleans after a massive evacuation, which was kind of like a practice run for the city. Now, if you know that New Orleans is barely above sea level, it uses levees to keep the Mississippi River out. And so it's a lot of it is very low elevation. So with the storm surge and all the rain, it just filled in like a bathtub. So the water and floods have always been part of the life in New Orleans. There's 3 centuries of floods from rivers and hurricanes. Billions of dollars have been spent on levees. It's a city built on a delta, which is a very loose mixture of sand, mud, and water deposited by the Mississippi River. So, this is a very precarious area. The deltas, they naturally subside over time as the sediment compacts. And the city has subsided 6 meters below the sea level and continues to subside. Levees prevent flooding, and therefore they also prevent the deposition of new layers of sand and mud that would build up the land level. And so as a result, it creates this bowl with the lake and river water levels higher than the city itself. So you have this lake over here and Mississippi River over there, Gulf of Mexico over here. And the city is actually this very low, it's this depressed region in elevation. So it just filled in like a bathtub. And so the subsidence will continue. So there's no easy solution. So it's a very unprotectable location. Then another example is Hugo in 1989 in Charleston, South Carolina, which was ruined several years earlier by the Civil War and severely damaged by an 1886 earthquake. and experienced the 10th strongest U.S. hurricane in 1989. A 5.2 meter storm surge with 220-kilometer-per-hour winds measured at Fort Sumter. It passed by Charlotte, North Carolina with tropical storm intensity and into the Appalachians as it was losing status, dissipating. The rains ranged from New York to Canada as it continued to drop the rest of its moisture. So we have this evacuation dilemma with hurricanes. So satellite photos allow warning of hurricanes making landfall so that we can evacuate people. However, there's about 50 million people that live in the Atlantic Ocean or Gulf of Mexico coastline counties. The population growth is faster than the construction of new roads and bridges that are needed to evacuate these large populations. Part of this is aided by the assurance of the federal disaster assistance. And so the warnings of 1999 Hurricane Floyd hitting South Carolina created massive gridlock, leaving people exposed on roads. Hurricane Floyd actually hit North Carolina instead. And so the dilemma for evacuation is that it's estimated 72 hours to evacuate most major cities. However, the hurricane path is not well known 72 hours in advance. So there's often not enough time to completely evacuate a large metropolitan area. There's not enough time. Once we have a good idea of where the storm's going to make landfall, there's often not enough time to evacuate a large metropolitan region. So there's other ways of mitigation. So we can alter the building codes. After many manufactured homes were destroyed in 1992, Hurricane Andrew, tougher building codes are enacted. New manufactured homes, they survived the hurricanes of 2004. As far as roof construction, the first step in destroying a building is often to lift off the roof. This can be prevented by elimination of strengthening of eaves, strapped roofs to walls, and band stapled asphalt roofing sheets on plywood. Build more durable, basically steady roofs. The impact also of wind-borne debris. So windows made of shatterproof glass or protected by shutters or plywood. Also remove loose objects from outside. And then there's the land use planning. So low-lying coastal land, it should be used for parks, farm fields, golf courses, nature preserves, etc., where flooding is not going to do as much damage. And in place coastal development restrictions. There's currently a building boom on shorelines. Thousands of new homes are built since the last hurricane strike, often in many shorelines. FEMA estimates over the next 60 years, 25% of houses will be 150 meters of a shoreline will fall into the water during some hurricane without mitigation actions. So the federal subsidies of flood insurance, which have just expired and are being phased out, those helped, I guess, they didn't act as a disincentive, right? That helped people build in these coastal regions that are at risk. And then the assurance that the federal emergency management funds would help pay for losses also didn't discourage people from building on coasts that are prone to hurricanes. So we need better public policy as far as how we are going to handle development along coasts. We cannot absorb the losses as a society for these people. I know it sounds unfortunate, but the more you absorb the losses, more people are going to continue to live there, and the more losses are going to continue to occur. So, one idea is if someone incurs a loss, you can help as a society make them whole again due to natural disaster, but under the stipulation that they have to rebuild somewhere else that's not at such high of a risk. And so as the sea levels continue to rise, The beaches can move inland by 1,000 feet in low-lying areas, and so the continuing buildup of houses along the coastline is just asking for trouble because the sea level is getting even closer and closer to our structures. The storm surge is going to go even further inland, more flooding, and so the ocean's coming to us, right? We're building closer to the ocean, and the ocean's coming closer to us, and so it's just asking for trouble. So all this development along this barrier island, a hurricane hits here, there's nothing to protect this, right? This is going to take the full brunt of that hurricane. And so, we should, in the future, if a hurricane does hit here, not rebuild this, right? Not rebuild this, because why rebuild it just for it to happen again? We should use this land for a different use, like a park, a golf course, or something. But we should not build there and then expect U.S. taxpayers to pay for the losses incurred by people building in high hazard regions. That concludes our lecture on hurricanes. Thank you very much.